the organizers for invitation. I really enjoyed all the great talks in this conference. And today I will introduce the adaptive dynamics and its concepts, and without avoiding hard analysis. And I hope it will give you some inspiration on your work in this perspective. Okay, the traits or the phenotype of individuals. So where they come from? We believe that it comes from genotype or DNA. Right? And how they can change? It changes by the sexual reproduction. So sexual reproduction combines two genotypes to produce a new genotype. But as we know, the relation between the genotype and phenotype is very difficult to verify. So we know DNA, but we don't know what will come as a product. So we may simplify the genotype, or even further, we may ignore them at all. So let's take the second perspective. So here, we'll ignore the genes and sexes altogether and only consider the phenotypic evolution. So in this conference, I guess everyone is considering only the phenotype. So we are considering the phenotypic evolution already. And then, how can a new trait arise? Here we assume new traits arise only from a relatively small mutations, layer mutations. Layer and small is different, but okay, layer mutation. So it mutates a little bit mysterious area, and we can find a new trait. Okay, then also we have another evolutionary strategy. We have mutation, and along with it, we have another evolutionary strategy, which is survival of fittest says. It's kind of survival of fittest says if the environment is given, then there is an optimal optimal strategy or the fittest trait. But in fact, the environment itself is influenced by the individuals. So environment decides the individuals, the strategy, and individuals also determine the environment, change the environment, and the change the environment also change the individuals. So this kind of loop is called the ecological feedback loop. So the adaptive dynamics, AD, its focus is this ecological feedback loop. So adaptive dynamics is considering phenotypic evolution with the ecological feedback loop. That is adaptive dynamics. And its main interest is to find a condition under which a successful mutant outcompete resident. So when a mutant can beat the resident, beat the already given strategy. Let's start with a simple example. The chemostat. The chemostat is a laboratory device to culture microorganisms. So we have a vessel, volume is equal to 1. They containing resources S and microorganisms with concentration X. And we constantly pumped resources with the concentration S naught with a rate D. So constantly the resources pumped in, and also constantly the fluid is pumped out. So the total volume is preserved, and something will happen in this range. So we are in fact feeding the microorganisms with the resources and observe the evolution of this concentration. How can we model it? We assume its microorganisms consumes the resource at the rate G, and we assume this rate G, so uptake rate G is proportional to S. So if there are many resources, then they in much, and if not, there is a little. Also, we assume the consumed resource is immediately transformed into new microorganisms. That means the reproduction is immediate. So we assume. And the reproduction rate or the conversion efficiency eta is given. So this eta means how much they reproduce. So the model is this: inflow of the resource and outflow of the resource, and also it is depleted by the consumption of microorganisms. And also population is decreased because it pumped out, and it increased with respect to reproduction. So this GS is the uptake rate, and eta is how much they reproduce. It means how much they reproduce. Here, for now, assume we are considering the environment condition as the resource concentration S. So S is environment. Let's focus on S. Then if we adding the equation, then we can see that their amount converges to S naught. So they are bounded. So the quantities are bounded. Okay, good enough. So if this, so they converge to some values. Say S converges to S bar. And if this S bar is smaller than S naught, then XT, limit over XT will be positive. So it is a non-trivial state. If not, if S bar is bigger than S naught, then there will be no microorganisms. So that is not our concern, because that is not interesting. There is no microorganisms. So we assume that S bar, this limit state, is less than S0. Then the state is given as this one, right? Because if that is equal to 0, then we have this one. So please notice this condition. This is necessary. Okay, so we have equation, and now, so we have environment condition. Now we should have a trait, phenotype. So now consider eta here. The conversion efficiency as a trait of a microorganism. Then, how this trait can evolve by mutation and natural selection? So what will happen to the trait? So what is the fittest trait? So let's consider just intuitively. You can answer easily. Eta is the reproduction rate. So if reproduction rate is big, then you have many offsprings, so you have advantage on survival, right? So big eta is good. As big as eta, it is good enough. Good. So, okay, let's do the linear test. Assume the resident have trait eta of resident here, and environment condition is given by the previous relation, we have the corresponding environment relation, right? So if the most of microorganisms have this trait, then the environment condition will be determined by this one, right? And a mutant have eta invasion, then this exponent can be written as this. So now the environment condition as this, and we considering new trait, eta invasion. So if this is big, if this is positive, then the new mutant with this new trait will grow. So it will win. I don't know how much it will win, but it will win a certain amount. And also we know that this quantity. So when there is this amount of environment, and also we have the resident trait, then this quantity is equal to 0, because by definition, so I mean nothing happens. Nothing happens when we have resident strategy with corresponding environment. So then nothing happens. This means so nothing happens. So the coefficient is equal to 0. We say this quantity looks like this one. This quantity as an invasion exponent. So in this way, in this sense, right? Invasion exponent. Why exponent? Because it's corresponding to x. So e to the something of, right? So we say exponent. So what is this inequality mean? Same resident environment. So if eta invasion is large, then the invader wins. Right? So it's enough. So big eta is good. So this linear test says that eta will increase by the mutation and selection. So arbitrarily it will increase. In fact, it will increase to infinity. But it is a nonsense, right? So there is no trade with the infinite reproduction rate. So why? Okay, then let's consider a more interesting example. So this is quite a nonsense because there is no trade-off of big eta. So we don't lose anything even if we have a large reproduction rate. Okay, before proceed, let's consider question of mutual invariability of the coexistence. So okay, we know the new trait will win, but we don't know it coexists with already given legend or not. So to answer this question, we need to study the full competition model. So by adding two species to individuals with two different traits. So we make them compete. And then using the Frankel-Bennington theory, we can answer this question is no. So the successful invader always prevails and the trait substitution occurs. That means trait is substituted. So the given trait with the legend is changed into a new trait, and there will be no other traits. So there will be only one trait at each state. So that means the trait substitution. So there is no coexistence of individuals with different traits. Also, as you already have seen in Professor Liu's presentation in the first day, useful tool to graphically represent these changes in the trait due to mutation and selection is called pairwise invariability plot, PIP. So this plot looks like this. The horizontal axis means the residential trait, and the vertical line means the trait of the invader. Okay, then this diagonal line is a neutral line. That means at a certain point, they have same residential trait and same trait of invader, so nothing happens. So invader and the resident have the same trait, so nothing will happen. Also, we can see from the previous example, we can denote this on plus and minus. So what does it mean? The plus means the invader will win, and minus means the invader will lose. So, and now we consider mutation and selection process. So what is a mutation? How can we represent mutation in this graph? At a given legend strategy here, so this vertical line is a fixed legend strategy. And if a mutation occurs, then there will be another invader with different trait. So it will move over the downward vertically. So if it goes to downward, what will happen? If it goes downward, then this region is minus region, so invader will lose. So invader will disappear. That means it goes up again to the neutral line. So there will be no state on this region. If we go up side, then we know this plus region, so invader will win. And now it is natural selection works. So that means now we know that by the previous result, the invader will prevail. So the given residential trait will be defeated by the new invasion trait, and it will be substituted by this new trait. So it goes to the neutral line again by horizontal movement. So this kind of mutation selection will happen. So it goes to infinity. So adapted eta will be going to infinity. So it's nonsense. But so let's make the model more interestingly by adding a physiological costs. First, give the exact form of the uptake coefficient GS, right? This is monotone increasing with respect to S. So, okay, this is for convenience usual form. And now postulate the trade-off between the conversion efficiency and the uptake efficiency H1 over H. This 1 over H is now says how big is the uptake rate. So that means if someone concentrates on the reproduction, then it has no time to eat, and vice versa. So if you can eat, if you are concentrated on eating, then you have small time to reproduce. So this kind of thing. Then we know the state is satisfying this condition under this constraint. So we should remember this condition. Then we have a certain express form. Also, this by these postulations, we impose this H is monotone increasing in H. So H is proportional to eta. H is proportional to eta. Okay, if we draw this S bar explicitly, the graph looks like this. Let's look into this. So this condition means S bar should be less than S0. So in this graph, S0 region, so the down region is only meaningful. So downward is only meaningful. The above region, there will be no microorganisms, so it is meaningless. So we only consider this down region. Then we can see that the range of the trait, viable population traits, is bounded. Also, we have a global minimum eta hat. So if we treat the PIP, then it ranges from eta minimum to eta maximum. So only this range is meaningful. And we can see this graph suggests that there is another neutral curve connecting this point to this point. So there is another neutral curve. Why? Why? Because if we have a certain environmental condition, so for example S naught, then there is two traits, eta min and eta max. They are both adapted to those environments, so they can coexist, right? Because they also they are coexistence. So they can be in a neutral line. So that is by the invasion exponent equal to 0. So this situation means, this point means, when legends have trait eta max, and when invade this one eta min, then there will be no, then they will coexist. So this is neutral, and along all this line can be a neutral line. Also, this intersection point will be eta hat, because this eta hat and this constraint, right, there will be only one solution. There is only one solution. Also, using the invasion exponent, we can conclude that invader will be successful only if its environment is less than the legendary environment. So from the PIP, we conclude that, so using this invasion exponent, we can give the signs plus and minus. Then in this graph, we can conclude that this eta hat is unbeatable in the sense that any new mutation can arise, because mutation corresponds to vertical movement, but in the vertical region they will minus, so there will be no mutant. So it is unbeatable. Also, any trace subsequence converges to eta hat. Eta hat is the minimum S bar, because in this graph, so plus minus, so and here minus plus minus plus. So eta hat is attracting all the other traits. A trait such that when the monomorphic legend, so legend with only one trait, has it, then no rare mutants can be successful. So in this situation, we call it as an evolutionary stable strategy. So it's nothing but a steady state for the user ODS. But here stable is a bit of a misnomer, because this state can be a repeller rather than an attractor. So this is nothing to do with the stability of the point. It just that it is a steady state. So that means, in fact, we can construct some example to find unbeatable strategy, but it is a repeller. So tell me, what does that mean? Usually it's called the Garden of Eden. It's Garden of Eden. So the only way to achieve it is by creation of God. And all the other methods, we can never achieve the situation. So it is a steady state, but we can never achieve it. So in this sense, the eta in the project is called global ESS. Also, on ESS per se, nothing to do with optimality. Nothing to do with optimality. For example, in the UK, driving to the left is unbeatable, right? Everyone is driving to the left, but in the rest of Europe, they're driving to the right. So it is in this case, it is a matter of favor, without nothing to do optimality. Also, let me teach you familiar concept. In our example, invader wins if the environment condition is smaller than the legend strategy. So that means if we invade try to win, then they should deteriorate the environment. So in this sense, the environment goes to its minimum along this sequence, and this kind of situation called Personalization Principle. So mutation and selection leads to the worst possible environment. So it is quite natural, because if we compete each other regardless of environmental situation now, then we'll do everything to do. Right? And finally, the environmental situation will be the worst case. But not always, because in this situation, the order structure of the environment limits the possibility of ladder similarly. So order structure, environment condition is scalar S. So there is only two directions. So there is only real line. So the possibilities are quite small. So if we can extend, for example, vector Rn or something, then there will be much interesting situation without the Personalization Principle. Okay, now let's go into abstract examples and some other concepts. Here we let call the invasion exponent if it is population growth rate of a mutant with trait Y under environmental conditions as by the latent trait with X. So S sub X, Y means X is the latent trait and Y is a mutant trait. So if this is positive, then the mutant will win. If it's negative, then mutant will lose. So assume this one is given, invasion exponent is given. Then by definition, S sub X with X is equal to 0 because nothing will happen. Right? The trait is the same. And differentiate this one along with the line, the diagonal line, then we have this relation. And the second relation, we can see that the second order partial derivatives have a certain relation. So if we consider only two of them, then for example, the cross term is negligible. So because we can write it down as the other form. So for later use, let's say this one as C11, so X squared C11. This one is C22, so Y squared. And this one is C12 or C21. Then we can consider only C11 and C22 and ignore C12. Okay. So please tell me if you have any questions. Okay, now we'll consider selection gradient. X and Y. This is a PIP. X is a latent trait and Y is the mutant trait. And we have a neutral line, diagonal line. And at this neutral line, if we consider S sub X, if along this line this is positive and this is minus, then what does that mean? This means the trait will grow. The number of trait value will grow. So if Sx of Y with respect to Y, so vertical derivative with respect to x equal y is positive, then it will go. So this kind of information is contained in this quantity, so we call it this quantity the selection gradient, which determines the direction of the trait. But what if this value is equal to 0? Then we can say nothing, right? We can say nothing. So we call it a singular point because it is difficult. When it is difficult, we still is singular, right? So now let's say something about this singular point. And this is, in some sense, only quite meaningful point. So singular point is the point where the selection gradient vanishes. If S is smooth, and because this one has 0 at x, Sx or y will be of the form, this one. And so if we take the derivative, then selection gradient means this one. So if a single point, then this one should be 0. That means this function have another 0 near the singular point x bar. So that means there will be another curve of neutrality other than the diagonal line. So let's consider the previous. Yeah, okay. So in the previous example, we have PIP. So diagonal line is always of neutral, but near this point, we have another curve of neutrality. So we can see that this eta is a singular point. So this is in general. Now we can ask some interesting questions or natural questions. So when is the singular point? Singular point is unbeatable by the nearby strategy. So i.e. when is it ESS? Okay. Then because in this point a mutant arises from only the vertical line, if this one is always winner, then one condition can be minus and minus. So if they are all minus, then this singular point will be unbeatable. So also we know that this point, because this is a singular point, s equals 0, and this is minus minus, so this is a minimum. If furthermore, if this is this concave, so this is concave, then we can see this is unbeatable. So this is a general condition. So if second derivative of the invariant exponent is less than 1, then it is ESS. But this is a general condition. That means, yeah, if there is certain condition, C22 equals 0 and something happens with the high order derivative, but we will ignore it for now. So in this fashion, we can find some other questions too. So for example, when is it B an attractor? So then when is B attractor? But yeah, I'll just skip this part. So as we already can see similar fashion, we can lead to this conclusion. Interesting is branching condition. Branching means a change from a monomorphic to dimorphic population. So what does it mean? Now let's draw a graph. Here x is a trait, and this is now time t. And assume first we have a monomorphic state, so there will be only one trait, horizontal trait. And at a singular point, if we have two traits like this, then we call this point as a branching point. Branching point. So when does it happen? So let's consider about it. First, because this point is a attractor of the monomorphism, we need this EAS condition. And also, in this dimorphism case, it should be a repeller. So it's attractor for the monomorphism and repeller for the dimorphism. Okay, so if dimorphism arises with two, now we have two strategies, less than strategy x1, x2, then the inversion exponent can be written in this way. Also, by definition, x1 and x2 will be two zeros of this one because they are neutral situation. And if this x of x, the monomorphic inversion exponent looks like this, concave, and this singular concave, then by continuity, and this is 0 point regularization, the graph will look like this. That means it is increasing outside of x1 and x2 and decreasing inside. So the monomorphism will occur and it will diverging. So it will go the outside of x1 and x2. So the concavity of the S guarantees the diverging dimorphisms. So combining them, we can see the branching point occurs if under this condition. So, okay. And now let's consider a PDE model. So eventually interesting. Consider two substitutable resources S1, S2. Now we have two resources. And we consider the parameter eta and xi, the uptake coefficients, instead of conversion efficiency. So you're going to have conversion efficiency. Now we consider uptake coefficients, by which means if we multiply S1 and S2, then it is the uptake rate. So it is quite similar thing. So if we model it in a chemostat, then using by the uptake rate, S1 eta times X consumes the amount of consumed the resource S1. So we can model it in this way, that's sure. And now you make a PDE model using this one. How can you model it? Consider small n as the density of organism with the trait x and time t. So time t is natural, but here x is as a usual a trait, not space, but trait. So we are considering trait space. Then the then the equation becomes like this. So we are considering the evolution of at each trait. So in this situation, we have only one trait, but now we have a trait space, so we should integrate it with respect to the trait space. And also we add the mutation as a diffusion term for simplicity. We may add the mutation as an integral kernel, considering the probability density. Okay. All right. Then we assume the mutation is small, so it's quite natural, right? So add epsilon squared. That means the diffusion is ordered over epsilon, right? Because we have second derivatives. This is ordered over epsilon. And we also rescale this equation by epsilon t to observe the effect of mutations. So let me be clear. So this can be a little bit. So we should have time scaling because we have trait space x and super time, and we are considering, for example, quite heuristically, the mutation has scale over epsilon. So we can see that. So we can guess that to observe the effect of a mutation, it will take a time of order of 1 over epsilon. All right. So we should scale by. So for example, this one is 1. So that means 1 is like epsilon over t. So if we try to find the useful information, then we should consider this time scale instead of the original situation. So we scale it, and if we take the limit as epsilon goes to 0, then we can expect that the solution would be a direct mass, sum of direct masses instead of a function, right? Because that means when epsilon goes to 0, that means mutation and selection process has been completed. So if it has been completed, then the survival of fitness, so fitness arises, one or several fitness arises. So this one will be no longer a function, but a measure Okay, so to catch this drag mass dynamics, we introduce the phase function like this one because we can approximate the Gaussian function. We can approximate the drag mass as a Gaussian function in the form like this. So we consider this kind of form, and we have equation. So we have this equation, and taking the epsilon goes to formally, then this vanishes, and we have this form with a constraint. So this is called constraint Hamilton-Jacobi equation. So let me be clear what this condition means. Because we have this relation, if phi epsilon is positive, then epsilon goes to 0, it blows up, so it is meaningless. So it will not happen. Definitely it will not happen. So phi epsilon will be non-negative eventually. And also, this point was only meaningful because if this one is a minus, then it will vanishes, right? It will vanish. That means that is not our fittest. So the only meaningful position is this 0 point. Is only meaningful. Also, we assume this 0 point are always occurs because if not, there is no fitness. There is no fittest. So this is meaningless. So we can assume this one. So now we consider this equation. Also, as I said, if we consider this 0 point curve, then we can expect that n epsilon will converge to Dirac mass concentrate at this particular fittest with a concentration xt. Okay, let's see a little bit further. Because this is 0, and also it is global maximum because it is concentrate. Global minimum, so its special derivative is 0. Also, its total derivative t is 0, so its partial derivative is also 0. So in the original equation, at the maximum point, this one vanishes, so this quantity is equal to 0. Okay, so it is. Now you can see what happens here. So x bar is our residential trait in this equation. So let's define the invasion exponent as this one, so R. But here, x is incorporated in this S1x and S2x. So S1x, S2x are the amount of resources when the monomorphic resistance has trait x. So corresponding resources. But how can you determine the corresponding resource? Recall that in the original equation we have this relation, this equation. So if monomorphic resistance has trait x with the population x, then n will be concentrated at the particular point. So in fact, this integral goes down to this equality. So it comes down to exactly the same in the case of the ODE, right? Because it's monomorphic case. So we have show this, and also it is neutral, so this quantity should be 0. So we have 3 equations with 3 unknowns. So if we substitute this S1, S2 into this equation, we have this equation, and because the left-hand side is mountain decreasing and it is -1 for x infinity, so if we have a certain condition on the initial data or initial conditions, then we can solve this one. So we can find corresponding environment. So we can find the invasion exponent. So we can analyze it by classifying single limits, as I said before. So we can find evolution stable state, evolution attracting state at branching point. In fact, okay, so it's almost done, okay. In fact, Digman et al. Gave a concrete example in which they found the branching point using this condition. So we can invent an example to observe the branching point. And also they solved numerically the original equation and also the corresponding Hamilton-Jacobi equation. And they observed that this is one figure of them. The left-hand side is a contour of n, with trait space and time, trait and time. So we can observe that at point x equal 0.5, there is a branching. In fact, they built an example to set up to like this. And the equation for n and equation for phi, also we can observe that this Hamilton-Jacobi equation catches the evolution characteristic of the original equation very well. Right? So this Hamilton-Jacobi equation works well in this sense. So, okay. Okay, and then let me comment on something. So this talk is mostly based on Dingman's gentle introductory paper, Beginner's Guide to Adaptive Dynamics. Also, the numerical computation or the numerical algorithm, as I said, can be found in this example. And most importantly, mathematical issues along with the justifying the link process. So, how do we have some mathematical issues? Obviously, I did take this limit formally. So this is one issue, and also the analysis of the constraint Hamilton-Jacobi is also one issue, and the other things in topics of adaptive dynamics is also an issue. So this kind of mathematical issues can be found for Simon Barnes' equation, and this will be a good starting point, as I think. So you can find the citations, we can find references there. So that's in my talk. Thank you.